Hi everyone. We'll now start another section that explains the Nebuli in stellar systems. And our first speaker is Howard Chu, and she'll talk about the cells views of planetary nebulae in the Magellan Clouds.
Yes. So I'm really happy to be here. I haven't been to any TN meeting for a long time, so it's about time to see everybody again. Okay. So this is the Magellan Cloud, and this picture comes from MCELS, the Magellan Clouds Emission Line Survey. This is a picture. This is the data we're taking in the 1990s. So it has been about 30 years. Okay, it has been about 30 years, and this is the MCELS data we love and we use it all the time. But then when you see the amateurs taking pictures like this, you look at this comparison, you're just like, oh my God, we're doing so much worse than the amateurs. That's really bad. We have to do better. Okay. So the solution to this is we use a dark energy camera and 4 meter telescope to not to beat them, try to complement them. And so this new survey is called DAMCEL. It's using Blanco 4 meter telescope. The field, so using a dark energy camera, the field of view is about 2 degrees compared to the MCELS. MCELS use a 0.6 meter Curtis Schmidt telescope. The field of view is smaller, and look at the pixel size. The MCELS has a 0.27 arc second per pixel, and MCELS has a 2.3 arc second per pixel. Right there, you see the resolution is a lot higher. And the MCELS image is the picture is really seeing limited about 1.4 arc second or better. And MCELS, where you look at the pixel size is 2.3 arc second, so seeing doesn't matter. MCELS has the H alpha O3 sulfur 2 and continuum images, and the PI is Chris Smith. And DAMCEL has H alpha and sulfur 2 and red continuum. But O3 and green continuum are ongoing, so we're doing it this year. But the H alpha sulfur 2 and red continuum are already done. It's all put on the web, and the data are all available from this website. Okay, and the paper for the large Magellan Cloud was published by here, Points et al. Just last year. Okay. So these are the fields. So the LMC is covered by all these fields. And so I always say, so you know all these colors. These colors represent different degrees of completeness, but in fact, it's only completed. For H alpha line and sulfur 2 line and red continuum, it's all complete. So it's all green now. And O3 and green continuum, they are still all red because of no data yet. We're doing it this fall. All right. And the detection limit is emission measure about 16. So I would like to be more sensitive, but this is the best we can do. All right. So to show you the comparison between the MCELS and DAMCELS, on the top there's an MCELS image and at the bottom is the DAMCELS image. And this is a picture of the Honeycomb Nebula. You look at MCELS image, you say, why do you call it Honeycomb Nebula? And when you look at DAMCELS, you know, yeah, honeycomb, yeah, right there. Okay, so this is a comparison for the supernova remnant. Then compare, this This is the supernova, this is the Planck Nebula in the Small Magic Cloud. So Jacobi and DeMarco did the survey in using ESO 2.2 meter telescope. So they have like a they show this of Planck Nebula, and for the same nebula using Damsel's image, we see this. Okay, this is the same scale, so it's much better. Okay, I'm not saying we're better than them, just that helps them. Yeah, it's really the equivalent. It's so much better. You know, I don't take any credit. It's the advancement of instrumentation. Okay, so for more details, you can look at the paper, and then to download data, go there and download data. Okay, now come to the main topic. So there's a look at the Planck nebulae. So first I give you a tiny tutorial. For the large Magic Cloud, 1 arcsecond is equal to 0.24 parsec. For the small Magic Cloud is 0.29 parsec. So for this kind of resolution, at the core will not be, the PN core will not be resolved, but the halo can be resolved. Okay. Now another little tutorial about Planck nebula size. This is the Helix Nebula. So this is like 0.8 parsec. And this big thing is a 3 parsec. So you know the halo is 3 parsec, no problem. Okay. And this is the nearest Planck nebula, sharpness is 216. So from here it's a 3. You know the degrees, like say in our galaxy. It's 3.5 parsec. So you know things 3.5 parsec, that's possible. Okay. So all right. So Reed and Parker in 2006 did this a Planck nebula sample. So we used it as benchmark. That was the best catalog of Planck nebulae in the large and small Magic Clouds. Large Magic Cloud is a very large galaxy, so many fields. What I'm going to show you is only one field. This I've only done this. I spent 4 days. Okay, I don't use computer. I use my eyes to look at. To search for resolved objects, okay, forget about AI, forget about computer, okay, my eyes are better than your computer. So, okay, 4 days and very sore neck, you know, I bent my head. And so in the following, I can show you a lot of pictures, pretty pictures. And I do you a favor, I put nice boxes, like every red box is 2.5 parsec by 2.5 parsec. Okay, so you can compare them easily. All right, so I show you all the Reed and Parker 2006 Planck nebulae. These are all known Planck nebulae. Starting from small size and to large. Okay, so these are kind of end result, big block. Okay, and this one, look at this, the central star is so bright. It's actually kind of an initialized star. I don't know what it's doing there. Initialized star with it's a Planck nebula. I don't know. Okay. And this one too, the very bright central star, what is it doing? Maybe it's core, I don't know. But okay, when you get to here, you can see, nebula resolved, okay? Nice. And then you get to larger nebula, you can see all kind of morphology and getting more and more resolved. And remember the box at 2.5 parsec, these are all allowed, okay? And Helix nebula is kind of the size, and the sharpness 216, even bigger than that. So there's no problem, all right? You see a lot of binebular structure like this, you see, you know, two lobes like that, and you know, all kind of the kind of typical Planck nebula you love and you like to see. And this one looks like a swallow or something. All right. Now getting to bigger thing. Remember the box is 2.5 parsec, so they still okay. These look kind of okay. They're large and fainter. They're okay. But then when you get to here, this become very kind of uncoverable. This one is maybe okay, but this is probably not okay. 2.5 parsecs. So actually, these were catalogs of 3. Oh, of course, they're not stupid. They say these are candidates. Okay. And they didn't say these are confirmed. They just said these are candidates possible. But when you look at this large picture, we resolve them. They say, I don't know what they are. I really don't know what they are. And this one is pretty large, 2.5 parsecs, and this is about, we're talking about 5 parsecs. And this kind of morphology, it's not anything like I've seen before. The next one is even crazier. Okay, so these are the RP 2006 catalog of the objects, and you see all these streets. It looks like the octopus. And I don't know what is the heavenly octopus doing there. Okay, then Now, there are two sources look like this. This is huge, 2.5 parsecs here. But we're talking about something like 7, 8 parsecs, big one. And you look at morphology, it quacks like a duck, right? It looks like duck and quacks like a duck, but it's not duck, it's too large. And this one is also kind of large. Now remember, sometimes there are other kind of imposters. So this is H2 region. You look at the morphology. Oh, it looks like PN. Hey, this one. Oh, this one. Look at the inside. This is the inner part. Looks like bipolar, and then outside they have a different direction bipolar. It's a young scale object. So these are young stars. Okay, they are not planet nebula. Have nothing to do with planet nebula. So you know that size does matter. Okay, the young stars they make big nebulae like this. Okay, and then here this is bizarre. So this is 2.5 parsecs, okay? Light exposure and deeper exposure, you can see these tails. And so this box is right here. And you look at fainter detail outside. Are these large scale outflow? I don't know. It needs to be confirmed. Okay, so those are things that we already knew. So those are known knowns, okay? Now I want to see the unknowns. So these are the new PN we see. These are the objects I'm gonna show you are not in any catalog. Essential star and no. So they're essentially they are not in SIMBAC. Okay, they're not in SIMBAC. Okay. So here are the image. You look at that. Hey, it's a blob. These are the faint blobs. They're just like Sharp 216. So no problem. Okay. So these are the probably faint evolved planet nebula. And here's this thing that's pretty bright. And with a bright central star, I don't know what's going on there. And here's another one, very bright. And the other is kind of very faint. Okay, good, big evolved planet nebulae. The size is still okay, smaller than 2. Then you come to this one. This was on my cover. And look at this thing. There's a star here and there's no star here. Okay, and this thing looks like figure 8. And it's technically H alpha and alpha 2, not in continuum. It's not an artifact. We look at the long exposure, short exposure, and this and that, it's always there. So it's real. Then we have this funny shaped thing. But these are still kind of a classical planet nebula shape. So these are still okay. These are all good. Then we come to bigger objects and see that it's beautiful objects, right? They're beautiful. It's just a classical PN morphology. Okay, so these are all kind of okay, but when you get to the large ones, they say, that doesn't look okay. It's too big. This is too big. So this one looks like, so the size here is, we're talking about something like 6, 7 parsec. So it's probably wind-blown bubble, but the central star definitely is not planet nebula. This is not planet nebula. It's probably some kind of some star. Now here comes the interesting thing. So there are these two nebulae. Okay, and that's small. So this side, the box size here is different. Okay, this box size is 6 parsec by 6 parsec. You see this nice nebula, and the central star, not eclipsing virus. They say, oh, you only have 2 cases, so what's the big deal? Well, actually, there are more. Okay, there are more in the large dimension color. I don't have pictures here to show you, but I have one slide ready-made long time ago. It's for the SMC. You look at it. This is from small dimension color. H alpha image, alpha 2 image, and red continue. You see this? This is one nebula. The central stars are all eclipsing binaries. And with the period about a couple of days. These are real things, especially for this guy. You know, it has two eclipses, and the phase shifts. So apparently there must be a third body there. So it's a very complex system. So what are they doing? So why do they shed mass like this? It's not shell. It looks like just blob, like a ball of gas. Okay, so these small nebulae around eclipsing binaries, they're found both in the large magnitude cloud and small magnitude cloud. Okay, so actually we started to do this because I want the students to say, so you know, when the Wolf-Rayet stars, the OB stars and LBBs, they all have small nebulae around them. Now let's go find small nebulae with unknown central stars, and that's what we found. Eclipsing binary. It's a new class of object. Well, it's not a new class of objects, but I don't know if it's for the first time, see so many of these with this kind of nebula around eclipsing binaries. It's very exciting. So here's my summary. So DEM cell survey is available, please use it. And the number of large PN we found for the new objects in the RP 2006 sample of about comparable numbers. So we're finding a lot of new objects. The very large cases, they may not be planetary nebulae. Okay. And the extended features are detected on planetary nebulae, and nebulae associated with the eclipse binaries are very exciting. So that's all.
Questions, first one?
Right, thanks, great talk. It's great to see the DEM cell survey producing such great data compared to what we have to work with. It's far superior. Not surprising you're discovering new things, of course. About the size of that red box, I think we might need to revise that slightly larger because it's clear from some of the very
You
deep.
know, when I make the box,
Yeah.
I was jet lag. And I thought in SO image, the box, it's a half the size. So I used 10.4 arc second. And that's actually the real size. I really want 20.8. I want 5 parsec box, but I already done half of it. I said,
Yeah, my point is that a lot of deep surveys have been done, especially by amateurs now, showing that you even take
Yeah.
a known PN, they're finding very, very faint stuff, at very large distance.
DEM cell is not deep enough. Amateurs still win. They still win. They're great.
500 hours, 100.
Yeah.
Well, I think that is first step, then we will then run.
I was wondering, if with finding nebulae around eclipsing binaries, would you be able to use the eclipsing binaries to learn more about the nebula than you otherwise would?
Wait, I'm not expert on stars. Single stars may be okay, but binaries, yeah. My knowledge is limited to carinosyly, no. I can do a Kepler's third law, that's about it.
So you have one question here and another there, Albert?
Thank you for a very nice talk. Regarding the large halos in the galaxy, they're very faint
Mhm.
and they're completely outshone by the center of the system. But in your objects, the halos seem to be dominant. Why is
I'm
this?
not sure they're halos, you know, they may not be, it's just large evolved objects.
So are these objects that we're missing in the galaxy?
In large galaxies, we don't know the distance, so even if they are there, we probably don't know.
So
And
let's
also the galaxies are extinction, there's hardly any extinction there.
Okay, this question.
Super quick question. So these are doubling the numbers of candidates.
Yeah.
So
It will be.
you're following up.
No. The small ones, we don't know. The small ones we cannot resolve, so we cannot do the small and resolve yet. But for the large ones, yes, we are doubling the number.
Okay, let's thank our speaker. Now you pause. This will now have Giovanna Liberati talking about plant and nebulae as tracers of the dynamical and chemical evolution of nearby planets.
So hi everyone, my name is Giovanna. I'm a master's student at Valongo Observatory in Brazil, and I'm very happy to be here. So thank you to the organizers for this opportunity. And I'm going to present my master's project entitled Planetary Nebula Tracers of Dynamical and Chemical Evolution of Nearby Spiral Galaxies. This project is being developed under the advisement of Professor Denise Gonçalves and Ariana Cortez. Okay, so I'll not spend time telling you what's a planetary nebula, but I want to point out that they can be excellent tracers of their host galaxy properties, and especially because they can be found even in the outskirts of the galaxy. So Our idea for this project is to do that, to study the planetary nebulae population of these two galaxies, M33 and MGC91, to see what we can infer from the galaxy from their planetary nebulae population. So M33 is a spiral galaxy here in the local group with M31 and the Milky Way. They are the three largest spiral in the group. And our idea, but the planetary nebulae population, although there are a few studies about them, they are not very much explored in comparison with M31, for example. And our idea is to use photometric data, the J+ data that I'm going to talk in a little bit, to see what we can infer from what we can explore of the planetary nebulae population of this galaxy. For the other one, MGC91, also a spiral galaxy, not in the local group, but nearby, and it's an edge-on spiral galaxy. And for this galaxy, we're going to use spectroscopic data from the Planetary Nebula Spectrograph obtained by Professor Ariana and collaborators a while ago to see what properties of the galaxy we can infer from them. Okay, so I'll talk first and mostly about M33 because this part of the project we are finishing now and we just started to work with MGC91. Okay, so as I told before, we are using J+ data. J+ is a photometric survey with 12 bands that you can see here. And because of its filter systems, it is extensively used to explore H-alpha emitters, to study H-alpha emitters. So we started gathering the planetary nebulae population of M33 from these papers, and we end up with 143 spectroscopically confirmed planetary nebulae that you can see here in red. So doing a cross-match with J+ catalog, we were able to find only 13 of them, marked in yellow there, cataloged on J+. So it's a very few. In order to obtain J+ data for more planetary nebulae of M33, we use Sextractor. There is a software to extract sources from astronomical images. And here we have the 3 J+ images that we use to cover the galaxy. Here in an example, it's H-alpha, but we did that for the 12 filters. And after some parameter testing and also deciding to use H-alpha as the detection image, which means that we detect the sources in the H-alpha images, and then we do the photometry for the other ones, the 12 filters. So after that, we end up with 98 non-planetary nebula recovered instead of only 13. And here we have a complete picture with in blue the 98 planetary nebula that we recovered, in yellow the 13 catalog, and it's worth mentioning that we recovered the 13 planetary nebulae that are cataloged using our method as well. And in red, we have the remaining 45 planetary nebulae that we can recover. But while we were testing which detecting image to use, I also tested some stacking images. And we stick to H-alpha because the recovery number of planetary nebulae was higher. But using some stacking images, we recover less planetary nebulae, but also different ones, some different ones. So this is probably a future work that we can do to recover even more and to see what planetary nebulae we recover from each image. Okay, so some aperture magnitudes have large errors, so we decided to use PSFX. That's also a software that can be used to build a PSF model, and then we run Sextractor with it to obtain the PSF photometry. So here we have this parameter space with Maggialto and flux radius, and we select stars to build the PSF model from this region here in red, avoiding saturated sources, extended objects, and possible cosmic rays. We also apply a limit of 0.2 to the error in Maggialto, class star greater than 0.7, because close to 1 means point source, and close to 0 means extended objects, and flags equals to 0, that also mean point-like sources. Okay, so we can do a comparison between our magnitude here and the J+ magnitude for the 13 catalog sources. And in the dotted line, we have the standard deviation, so we can see that they behave quite well, except for fainter magnitudes that we have a difference of almost 1. Okay, so having these magnitudes, we decide to plot them on color diagrams, these 4 color diagrams that you can see here, proposed by Gutierrez Souto and collaborators. And we also plot this criteria that they developed to select, to search for halo planetary nebulae in the Milky Way to assess the possibility that some of these planetary nebulae might belong to the halo. Okay, so here we have the four color diagrams. The gray clouds in the back are the extracted sources from the images. In red, we have the planetary nebula. In yellow, we have 5 planetary nebula that meet the criteria of the 4 color diagram at the same time. In blue, this blue dot here is 1 planetary nebula that, according to Sardou and collaborators, could be from the halo of the galaxy of M33. And in purple, we have extracted sources that also met the criteria for all the diagrams that we thought it might be worth to take a look into that. So first we start looking at the 5 planetary nebulae that made the color criteria. So here we have their J plus SEDs, but we can't infer much about their belonging with the halo or the disk of the galaxy from this. So we decided to do as well a simple velocity study of them. So here we have the velocity of the planetary nebulae and minus the systemic velocity of the galaxy. In red, again, the planetary nebula. Here we have only 4 of the 5 planetary nebula passing the criteria, because for one of them we didn't have velocity measures. And in blue, also still the one possible halo according to Sardou. And in here, in the simple model, we would expect the halo planetary nebulae would lie around 0, this black line, but this only happens for one of these that we are analyzing here. But as I said, it's a simple model. Okay, moving on to the 16 extracted sources that we thought it was worth investigating as well. Most of them turned out to be H2 regions. Most of them are classified as H2 region. One of them was in Magrini's list of emission line objects. We also found some globular clusters, and for one of them, we didn't find any information, so still could be a planetary nebula candidate. And yeah, so we investigate the planetary nebula population of M33 with J plus data. We were able to recover photometric data for 98 previously known planetary nebula instead of only 13 that were originally in the catalog. And we can conclude that J plus is good to study, to recover, to characterize this planetary nebulae, although it is not specifically optimized to do that. We need to use a subtractor with different parameters to obtain more planetary nebulae. And investigating these sources that met the criteria, the 16 sources, we know the combination of these criteria from the diagrams, it's a powerful tool to identify H-alpha emitters, not necessarily a planetary nebula. Okay, and combining with the kinematic information, our analysis indicate that only one of those 5 planetary nebulae passing the halo criteria could be associated with M33 halo, which is actually expected since the stellar halo contributes very little to the galaxy luminosity. So we believe that the bulk of the planetary nebula population, at least these ones traced from J+, belongs to the disk of M33. So about NGC91, I'll talk just a little bit about. As I told you, we are going to use data from the planetary nebula spectrograph. We have the images, we have the extracted catalogs, and we are working on the completeness of this catalog. So we insert artificial sources to the images to extract them. And these sources are brighter than a limit magnitude that recovers 80% of the planetary nebulae. So we can assume that any loss in detection is due to contamination from the galaxy and stellar contamination. And we are seeing here the recovered fraction of planetary nebula for different distance from the center of the galaxy. So this gives us a factor that we need to apply to correct for completeness of our sample, and this is what we are doing now. So just to share with you our goals, we can talk more later if you want to know more. But our goals is to explore the nature of the thick disk of this galaxy, and if it is associated with a merge event, study the asymmetry distribution of the planetary nebulae, and combine the kinematics of the planetary nebulae with the galaxy light distribution to recover what fraction of the galaxy light is associated with each component of the galaxy, and combine our catalog with this other one from this work, and compare the distribution with the distribution of each one. So that's it. Thank you.
Thanks, we'll take the time for questions. Luana?
Yes, all these PN identified in exogalactic systems, because we can't actually, when they're so far away, get any kind of morphological information for them. All we have is limited spectroscopy. Now, I know that from Granticam 10 meter, Guanfang has shown that you get decent spectra for some of them, and indeed identify helium-2 and supplies like that, which kind of confirms the PN. But a lot of the earlier work based on on-band, off-band, or O3, you're making some assumptions. So we already know from our own galaxy, there's a hell of a lot of imposters out there, which look and smell like PM, crack like ducks, but are some other waddling creature. But we'll like those. So just be careful that just because they're not necessarily PM, they're just initialized objects or something.
Or. Yeah. Stavros?
Thank you, Giovanna. Nice work. My question is the missing sources, the missing PNF from the catalog. Have you checked if they are faint enough for the J polars?
Yeah, I was going to put a spot here, but I thought it was going to be a lot. But yeah, we did this study, and we first assumed that was the case, but it's not. We are recovering some planetary nebula that are actually fainter than some of these that we are now recovering, and we think that we're not recovering this one for a variety of reasons, but in some cases they seem to lie on top of spiral arms, so maybe a lot of contamination is behind it. It's behind this reason, but I don't know. But they are not the fainters.
Any other question for Giovanna? If not, I do have a question. I heard for a while that these multiband photometric surveys and large areas would be really important to find these kind of objects. What's the reason that we have an idea what is the reason why we haven't, instead of the 2-3 bands that you use in other like IFAS, BFAS class and all, why this one with 12 bands is not doing so much better work? Or it looks like it's not so much better. There any reason or some ways we could improve on this?
Yeah, because if we go back to the filters, we can see that we do have the H-alpha filter, it's great. But for example, this filter here is J0515. It recovers only a little bit of the O3 line, so it's not optimized for that. But if we use JPass, for example, that has way more filters, we can probably trace some more specific lines from planetary nebula, maybe helium. So yeah, from JPass, not JPass.
Yeah.
I have a comment. We are running a program, it's integrated telescope at Havalambra. It's called J-Alpha, to look for large field of view images of planetary nebulae, nova remnants, supernova. And in this case, in addition to the J0660 filter, we are also using the JP 500 filter, which is 150 Armstrong, covering the oxygen tree and each mission. And it's really producing very nice results.
That's very good stuff.
Yeah,
Just to make a comment, it will become at some moment. So, yeah.
I don't think this is how.
No, but 5C is right in the pipeline to reduce the data. So those are multi-position images that they are combined to have very flat sky. And so once that we have the DSS abstracted, and the data is fully calibrated, just a bit later, it's going to be made public.
Okay, let's thank our speaker. And now let's invite Vanna. So, uh, so now we have Vasilis Pekov talking about plant enabling star clusters, proving new constraints in low to intermediate mass stellar evolution studies.
Okay, so hello everyone. As Elise said, I'm Vasiliki Orvana, as most people know me, Fragu, and I'm a postdoc at the Local Observatory of the Federal University of Rio de Janeiro. Thank you very much, Martin, and all the committee for inviting us here. And I will talk about planetary nebula in star clusters and how these are providing new constraints in low to intermediate mass stellar evolution studies. So planetary nebula that belong to star clusters have the advantage to have some of the properties predetermined. These kind of properties can be the distances, environment, and ages. And as a result, they can help us determine very important of the properties that we cannot determine in other ways, as the mass percent of star, the progenitor mass, and those and such as the created direct link between initial and final planetary nebula properties, which is extremely important for stellar evolution studies. Some indicators, how can we actually define that the planetary nebula belongs to a cluster? Indicators can be the agreement of multiple cluster planetary nebula parameters, such as their projected positions on the sky, their distances, radiating, but most importantly, the radial velocities, because cluster stars have very low velocity dispersion, so they're typically less than 1 kilometer per second. Also, another indicator could be the atmospheric planetary nebula dimensions. Unfortunately, such cases are quite rare. And until today, there are only 4 such instances identified in our galaxy in globular clusters, in 5 in open clusters. Here, we'll talk about specifically the detections of planetary nebula in open clusters. Okay, the first case will be the planetary nebula PHR 1355 that belongs to the open cluster Andrew Lindsay 1. This is the first planetary nebula confirmed to be in an open cluster. It's a bipolar planetary nebula and was found to have an enhanced nitrogen and solid type 1 chemistry. You can see here an HST image, a 3-color image, where we can see the cluster, the center of the cluster of the planetary nebula is the nebulosity here, the blue nebulosity. You can see it's bipolar shape. With deep HST imaging, we're able to construct a cluster color magnitude diagram and to measure the cluster physical parameters, and also to measure the planetary nebula full size for the adopted distance to be 83 parsec. Here you can see an O3 HST image that we used to measure the size of the planetary nebula. Here. And then also HST imaging allowed us to identify the planetary nebula central star as the bluest star in the field and to measure its physical parameters. Here you can see a visual HST image central of the planetary nebula. The circle stars are the blue stars in the field, and the one circling red is the bluest star of all, and also the yellow line is the axis of the nebula. So you can see the red, the circle red, it's the bluest star in the field, and also is so closest to the nebular apparent center. And as such, this is our identified single star. We also found that the presence of an unresolved low mass companion is highly unlikely, and we estimated the central star progenitor mass to be around 2.5 solar masses, and its final mass 0.6 solar masses. Then we have the planetary nebula BMP J16135406 in the open cluster NGC 6067. Here we have an SHS image centered on the cluster, and you can see the nebulosity. Here it's on the north side. The planetary nebula, as you can see, it has a bipolar morphology and also type 1 chemistry. The progenitor mass was found to be around 5.6 solar masses, which is close to the theoretical limit of core collapse supernova formation, making it the most massive progenitor that has empirically confirmed to evolve the planetary nebula. And the final mass was estimated to be around 0.94 solar masses. Here, this is a 4:3 color image, so the identified central star centered in purple. The third case is a planetary nebula, I'm not going to pronounce this, in the open cluster M37. So the planetary nebula was detected from IFAS studies. It has a bipolar shape, also it has a neutron type 1 chemistry. It's very extended and faint. Here you can see the IFAS image. You can see the nebulosity is very, very faint. And the star circling blue is the identified central star. The kinematic age of the planetary nebula was found to be 78 kiloyears, which is the largest kinematic age found for a planetary nebula. So which indicates that in open clusters, planetary nebula do not dissipate as fast as huge planetary nebula. The central star, that identified central star, was also found to be a hot H deficient white dwarf with an effective temperature of 10 kilokelvin. It is also rotating variable with a period of around 0.5 days. Its initial mass was found to be around 2.8 solar masses, and its final mass around 0.6 solar masses. Then it's the planetary nebula NGC 2880, it's in the open cluster NGC 2880A. And this planetary nebula cluster members, it has long been debated in the literature. And finally, high resolution ghost from Gemini planetary nebula spectra has allowed us to confirm their association. The planetary nebula has a very complex morphology, a bipolar shape, and it has nitrogen type 1 chemistry. Here, this is an SHS image of the cluster and the planetary nebula on this side. You can see the complex morphology of the planetary nebula. This planetary nebula also is very well studied. Here you can see, so this is a typical ghost spectra, one of we used for to define the planetary nebula radial velocity. This is the same method that we used for the other planetary nebula clusters. So what we are actually doing, we're taking the high resolution spectra in different parts of the nebula, and then we use the most prominent lines, the N2 and H alpha, to measure the radial velocity, the mean radial velocity of the nebula. You can see here how there are double peaks in the lines. This is indicative of the high resolution spectra, such like each peak traces a different component of the nebula. And in this way, we can measure in high accuracy the radial velocity of the planetary nebula. So for this particular planetary nebula, its kinematic age was found to be 11 kiloyears. Its effective temperature 130 kilokelvin. Its initial mass, 13 kilokelvin. The initial mass 2.33 solar mass, and its final mass 0.558 solar masses. And then here is the latest detection, the latest discovery, the latest confirmation, and it's the planetary nebula PHR. Today, 1724-38-59, a member of the open cluster Stronghold 25. The planetary nebula has been identified through the SHS survey. It's a high resolution, it's high resolution HRS from SAL and GHOST from Gemini planetary nebula spectrum combined with Gaia DRC cluster data allowed us to confirm their association. The nebula has a butterfly-like shape, as you can see here in the SHS image. And its kinematic age was found to be around 23 kiloyears. of additional data from FORCE-2, with imaging and long-distance spectroscopy, allow the further exploration of the spectral profile and the identification of the central star. The spectral density was found to be in the low density limit, and ionized mass was found to be larger than 0.11 solar masses. And the reddening that was estimated from the color of the central star, the identified one, was found to be around 0.9. The visual magnitude of the central star was found to be 21.1, while the effective temperature 250 kilokelvin. The initial mass was found to be 5.12 solar masses, and its final mass 0.95. And note that the effective temperature 225 kilokelvin is 250 kilokelvin is the largest one found for a central star until now. Here you can see the visual image from FORCE-2. So the blue rectangle indicates the position in the shape of the planetary nebula, and the circle stars are the blue stars in the field. The one circling in blue is again the blue star in the field, so it's the identified superstar. We plotted our objects on the initial final mass relation from Cummings, and here the gray points are from Cummings, from cluster white dwarfs, and the color points are from planetary nebulae clusters. We can see that all our points from the planetary nebula fall around 0.1 solar mass below the general trend. So this is actually a systematic shift that needs to be further explored. We also plotted our points with the initial final mass relation from Marigo, and they found the kink between around the solar initial mass is 1.7, 2.2. So we can see that our polar points actually delineate this kink in a space that it's sparsely populated. As a summary of all our identified objects, we can see that all planetary nebulae are bipolar and have a type 1 chemistry. And also they tend to present some extremes, such as the largest kinematic age found for a planetary nebula, the largest initial mass confirmed empirically, and the largest superstar effective temperature. These things do highlight how important it is to study planetary nebulae in clusters. Our next steps would be to detect more such associations. There are more candidates pairs already identified. And also we all need to study in detail all the identified pairs with deep spectral photometry, photoionization of climatic model. And also we need to further explore the systematic effect in the final masses of planetary nebulae in open clusters. Thank you very much. Time for questions.
Yes, I'd just like to point out that the candidate in M37 was brought to my attention by David Fruth back in the day, when he saw emission lines in spectra of the stars that were done through fiber spectroscopy of the cluster. And apart from NC2818, of course, all the other candidates I found, when you were my PhD student, you were working with us on building all those papers up. So it's great work, Vanna. Good to see. It's like clarify that object.
These are important results. Obviously, it's great to have a sample of planetary nebulae in open clusters. You learn so much, as you're pointing out. You stress that you need agreement between the systematic velocity of the planetary and the cluster. In at least one of those cases, there's a bright CO line. That's NGC 2818. And you expect that, I think, in all of these objects for various reasons, that they should be molecule rich. And so it should be possible, I think. Could you comment just on the agreement that you've got so far in radial velocities?
The problem is that actually this planetary nebula are very, very faint. So we use the most prominent lines because these are the ones that have the highest signal noise ratio. And then we also, the spectrum we're getting is usually centered to these lines. We need to get these ones. But yes, we will try to explore better, but the problem is we need more telescope time and it will be difficult to find a better. Means what we are trying to do is to get abundances, but it's extremely difficult because
I guess I would encourage you to go after the CO and the other ones because I think you've got at least one great case you can compare with now. And these are exciting to look at.
thanks.
Thanks. But thank you for the presentation. Second, thank you for your work on this initial final masturbation because I love it and I find it really important. What I do. So my question is, in all these studies that you have performed, the initial mass that you get comes from the properties of the cluster
Yes.
under the assumption that they come from a cluster evolution.
Yes.
Is it? Okay. So that was just wanted to be sure about that. That's perfect. Thanks.
So there's another question here.
Thank you very much for your talk. I'm wondering about the location of this planetary nebula regarding the center of the cluster. They confine the center in the outskirts, and could it give us like the kinematics, the history of the cluster or something like that?
No, we haven't explored this yet. Yeah, we do know in the images where exactly they located in the apparent center. Some they are close to the center, some other a bit farther away. But we haven't performed any kinematic studies.
Okay, thank you.
We still have time for question. You have one there. Just a minute, wait for the microphone.
In the table you showed chemistry type. Did you use it was written type 1. Did you use nitrogen and oxygen ratio?
The ratio?
Okay.
It's in the table here. No, in the table here it's not, but wait. In this one I haven't noted here, but yeah, in one case, in the one in the NGC 6067, it was I measured the ratio and it was well in the ones expected. Well, at least using the Caracas onyx.
Okay, very few questions.
Yeah, so when you find planetary nebulae at the center of those clusters, is it possible they have had those stars some interactions with the environment so that they speed up or change their evolution time scale?
The one that we can see for sure, given the evolution of the planetary nebula.
Yeah.
The one because we measured the kinematic age of 78 per year, so one that's obvious that the planetary nebula do not dissipate very fast on the cluster.
No, but it is the evolution of the star of the
Of the star. No, we haven't checked that. We'll see. They are all bipolar though. So we need to find out why they are all bipolar.
Okay. That's the example. Now, I think what's it? Happy, Chappy. So now we have the visual charts talking about formation of highly positively charged fluids within planetary nebulae.
Yes, from both. Good morning, everyone, and good morning to beautiful city of the Granada. Happy from Hong Kong, postdoctoral fellow in Laboratory for Space Research. Quickly update you that we are right now focusing on 3 compact young PNs in terms of finding the highly ionized fluids. And in a couple of slides which I prepared, I updated that why we are so interested in these topics. And fluid is very special, of course, molecule. one out of 500 allotropes of the carbon that is already listed. The family is started from C20, 12 5-member rings, synthesized at 2000, gas phase, C30, C40, C60, and all of them, they have a very special characteristic in terms of their thermochemistry, bad for the planetary nebulae. They suck out all the energy from the planetary nebulae. Their heat of formation are absolutely mind-boggling positive among all the molecules that we know. So, for example, the formation of 240 grams of C20 in planetary nebulae can be equal to evaporation of 30 grams of the water. So that's the amount of the energy that the planetary nebulae can lost. Chemistry of them enhanced. So one of the characteristic features is that the neutral form, of course, the gas phase, fluorine is not that much reactive, even in presence of the radical, like the hydrogen radical. While when it is ionized, so not only the temperature of the reaction is dropping down, consistent with the interstellar dust. So also enhance, there is no high pressure, so with a little bit of the energy, the reactions with the other radicals is foreseen in the ionized form. So I give some quick introduction on the methodology that we have done. Possibility of formation of C60 with the highly ionized charge abnormally high, and our efforts to detect such cation, and the connection to our proposal, which we participate in cycle 3, cycle 4, and we are going to participate in cycle 5 as well. Plus the short white paper that we proposed to the Roman Grace SOC team. And of course, later on, I give some astrochemistry goals. But this is a quick timeline. C67 plus was detected 1994. So basically, the area of the chemistry, which was all confined on just +2 and +3, was completely changed because of the C60 polarity. So we shouldn't expect that such a molecule, or let's say the cation, could exist. And then in 1996, Cierlowski said that no, the limit is 10 plus, so we can't have the 10 plus. Experiment moved forward more than, let's say, beyond even the theory. They found that the C60 12 plus also can exist, and also the signature of C60 14 plus. So 14 electrons out of these molecules. So it is well beyond any kind of molecules that we know. Diaz said it at 14 plus. Handbook of Nanophysics Clusters and the Fullerene 2010, they pose a question that how many charges can C60 tolerate? And then we solved the riddle in 2021 by theoretical work, and we showed that C60 can tolerate up to 26 plus charge. So which means that it has a very, very tough molecule under the radiation. The radiation is something which is a lot in the planetary nebula. Okay, this is the way that we go. We use electron density as a backbone of our computational methods. Say DFT is based on electron density. We have the means of very strange theory of quantum theory of atoms and molecules in order to check that when the molecule is ionized, still the carbons are added together or attached together by the bonds or not. Then we detected it with different ways. If there are those green dots between the carbon, which means that they are attached to each other. If the carbons are talking to each other as a ring, we find a red. And if the cage, which is all 60 are talking to each other, stay as a cage, we can find the blue bond. The blue bond. So we found in all 26 species, Catarrhinic species, all share the same features as their parent. This is very important because of the lifetime of the fullerene will dictate the lifetime of the fullerene, chemical reactivity and fragmentation. And that's finding these species were very important because they led us to have some mechanistic approach, understanding that what is happening. So we propose a pathway to the formation of this pathway. And that is a single photon ionization. Calculate each step of the ionization from 1 to 26. The range is between 7.8 to 82.44 electron volt, all in the UV, still in the UV range. Now the change, as you can see, the change in the molecule, I put it in a change in the volume, and it is absolutely fascinating. So you have the molecule which is shrink in size, then it doesn't have at some particular ionization, it doesn't change the size. Then it will start the expansion, then it's move out more than the volume that it started off, although it's losing the electron. So that's complete answer from quantum mechanics. And then you have the basically the no fullerene exists. So basically what is usually said explosion. Okay, this not explosion. And the last ionization here is 26, this line, and it is aliphatic. So like the 18, but it's in 3D. Okay, while the fullerene itself contribute to UIE bands of 7, 8.5, 17.4, 18.9, we calculated that contribution of these cations is from 1 plus to 6 plus, around 6 micron, 6.5 starting, without interfering with the PAH. So here I put all the experimental, observational, and also theoretical data here for this, for the infrared signature of the PAH to make sure that we can detect these patterns. Now we go to 10 plus, the IR spectrum getting much more interesting. You will have 2 bands for C60 10 plus. It is the only ion which carries the same symmetry as the fullerene, just only the size of the ball is smaller. That was why we call it buckyball in our publication. I am fanatically believe that in, okay, yes, that I have to move forward fanatically, which is 17 point. These 2 bands, okay, no problem. These 2 bands are there, always with the flare. It is somewhere there, and we can find it. More charges, more contribution to the longer wavelengths. UIE is 21 micron. This is a spectra of C60 26 plus, the highest charges molecule that you can find it in HCl. Now, it contributes to 11.2, surprisingly, without any hydrogen. It contributes to 16.4, contribute to 21.6, contribute even to 14, 41. They have the vibration, so the molecule exists on that level. So it is not just of the theory. I mean, we have a double confirmation from different theories that yes, and this is another 21 micron vibration of the molecule. So they absorb the energy and in this level. These 3. First one is P1 to one that we found the one or two, okay, this is a tentative, I said. I'm careful about not saying identification. Tentatively, we found the signature of a large number of them just under the plateaus of the 17 micron and the 19 micron. Is that true? Still, we have to search. And so, for example, the two bands of C60, 20 plus, match two of the UIEs. And the errors, I can say that is exactly even better than the errors of the bands that we assign to C60 itself, theoretically. We go to M4, 18, and we see something absolutely fantastic, because hopefully the Akari data will exist for this object. This object, which has a very high temperature at the center star, contains, we want to confirm 100% that it contains the fluorine and also the cationic form of the fluorine. In addition, the diagnostic part shows that there are some other organic molecules are within this planetary nebulae with the fluorine. This is a 3.3 with the signature of the aromatic compounds or aromatic bonds between carbon and hydrogen. And very interesting, large plateau, which the flux is almost, I can say by eyes, is half of the flux of the 3.3, and that's the signature of the aliphatic compound. Yes, I have done, I think I have, I'm going to say, and we suggested such coexistence between the fullerene, the complexity of the fullerene containing compounds in cycle 3. And okay, we carry on with the cycle 5 as well. Now, fragmentation. Now, the study gives us a very particular way of looking at fragmentation of fullerene in cold condition, not hot, based on ionization. That is a mechanistic approach. Now, I say that this is a plus 27 charge. So you knock out the electron from the last ionized form of the fullerene, you ended up with such fragmentation. Fragmentation is C2, then you have two C5, and then you have one jump of the fraction fragments, which is C48. C48 may have just 30 seconds. I stop, okay. And I stop here. The fragments, when I draw it in 2D, it is exactly the Maon precursor, which was proposed by Songkok and Yung Jang in 2011. So we have the story here. We can answer a lot of nice questions. We have a sample right now to say that yes, fullerene can coexist with the other complex organic molecule, and the story can be connected by understanding its cationic form. Okay, thank you very much. That's all.
So time for questions. We have the Ursula there. That's okay, you have time for two of them, so. Go ahead.
I was wondering, in one of these objects, for example, TC1, what's the likelihood of a fullerene encountering enough photons to get to such a high ionization state without encountering any electrons or other negatively charged species?
I don't have any answer to this question. Honestly.
So for synapse.
So there are rotational states as well, right? Are they for the structure?
Absolutely.
And they're inside the line, like they're less energetic. Does this erode vibrational?
Those ones that you have seen are the pure vibrational. We didn't add the rotational levels here. because they are very cold, the dust are very cold, so if those rotational level might be still not that much focus on the guys to get.
You have another question?
From the symmetry group of C60s, sorry, from the symmetry group of C60, you
Yes.
expect certain values of Q to be preferred. Do you see any of them? Like 2 and 12 are the obvious ones, but there must be more.
You mean the vibrational or rotational?
I just mean the configuration. I mean, C60 has a symmetry group, right?
That's right.
And you would expect certain values of Q to be preferred because they conform to that symmetry group. So 2, where you have two ones opposite, at 12, where you have the distribution of the pentagons.
Are we talking about the geometry one or
I'm basically talking about how you would distribute those charges over the surface.
Oh.
That's what
So
your value of Q, you
That's-
have to distribute something.
That's right. We use a quantum theory of atoms and molecules, which basically do the partitioning based on the symmetry of the molecule. So the partitioning into the atomic or topological atoms are encountered in all of them. So I have all the data, and the charges are exactly follow the symmetry. So explicitly, because the quantum theory of atoms and molecules is analyzing the electron density. So all the information of the full symmetry is implemented. And when we calculate it, we see that. If we don't see that, we say that, of course, the calculation is wrong. Thank you very much for the question. Yes. Yes.
We have another question here, just a minute for the microphone, so. And I can, then we attend the session. Here.
So high charge also mean that the atoms or molecules are bonded to fullerene in the exohedral form. I mean to the cage from outside, and these all give an outcome in the spectrum such that bumps occur or redshift or even sometimes blue shift, depending on the number of the atoms bonded to fullerene. So you have showed us some spectra of these highly charged fullerenes, but some of these, at least some of these, had to be bonded in the exohedral form from outside the cage, or in the middle of the cage, endohedral form. Then, if it is in the middle of the cage, you can detect the neutral ones, because if an atom like helium is bonded in the center, it will give out an like bump in the spectrum. So I just wonder which atoms or molecules, or have you ever detected these
Our approach is very pure, simple. So you have fullerene or any kind of molecule, you can practice it with the PAH, you can practice it with the benzene, you can practice it with any molecule. Just knocking out the electrons. And then do the computation to see that if the species is viable, which means that you can get the answers from quantum mechanics that such a group of atoms are forming a molecule and then forming the vibrational level. So here we just take the fullerene. I say that fullerenes. No heteroatom are involved here. Now the combination with the heteroatoms for forming the complex is another topic which needs a huge amount of other computation.
huge amount of
Definitely.
Yeah, in let's say in the observational area, you need to, in order to observe them, you need to find them together with other atoms or molecules linked to the cage.
Right.
Huge.
Right, that's another basically scenario which I think the people in Tenerife, my colleagues in Tenerife are following. Of course, the addition of the iron, exo or endofullerene compound, yes. Yes. My pleasure.
Okay, let's finish our. So now we start the recording. We have first questions and I don't know if you have any introduction, please.
Well, yeah, so just a little short introduction. So these meetings are characterized by a lot of time for discussion. So this is expected to be led by the chair of the organization, but also anyone in the room that has any comment on any of the talks that we have had so far can express themselves. And then let's the ball roll and let's see where it takes us. Okay, so I don't know whether you have some question to start or if there is any question in the room.
Yeah, even in the room, I don't know, but in the Slack, there is perhaps Ursula who started this. I see that, well, I see he saw that. We comment something there about starting the discussions, if you wanna.
Yeah, and you said we don't need more observation.
No.
Yeah, but it was there.
So
No, I do feel that.
Perhaps the microphone is.
I mean, it's more like an end of conference, type statement, right? But there is an awful lot we have already, and I always have this impression, since I started doing theory full time, I actually look at the surveys one after the other, there's always another one. And it always wants to do something else, and yet once the survey comes out, that some wonderful results are published, and then there's certainly much more in that survey that can be extracted, particularly in combination with other surveys. So I'd love to see, I mean, there's a lot of young people at this conference, which is wonderful to see. You guys, I am done, but you guys, there's an awful lot of knowledge in there, which I think we're kind of not getting, but it's probably embedded in the enormous amount of work and data that we have. So the question is, how do you extract multi-dimensional information? We have, of course, we already know that there's the projection. We know how to be project things more or less, right? So there's that dimension can be considered. Then there's a depth. You know, San's talk this morning was really great. There's so many dimensions within which you see this morphologies, but it can be collated, probably not by our brain, by our techniques. And of course, I'm going to say AI here as a very, very, very big overarching sort of word that takes LLMs as well as all the old MCs and all the techniques. But there certainly must be a way to collate this knowledge and extract more than we can do ourselves. And I haven't really seen a great deal of studies that use these techniques.
Yeah.
okay, there's
Yeah. Another question about this.
who has used AI for planetary nebulae? No, Quentin has, but he seems to have left again.
Well, I might Stavros to talk about this. Stavros, would you like to comment on this?
Yes.
You were the.
Even I'm not an expert on machine learning and AI. I just touched the surface. I do believe that we can combine information and data, even so far I've used that, magnitudes and colors to distinguish objects, emission line emitters, for example, and distinguish if they are symbiotic stars, planetary nebulae, H2 regions, supernova M. So definitely one thing is that combining information in different wavelength range from optical infrared is crucial, and it can help us to do something. So besides that, another very interesting work that I've read is about identifying planetary nebulae based on the morphology. Don't remember, it's not a simple machine learning, it's an AI. I don't remember the code. I think Parker was co-author. It's a very nice work, and they identified several weak pain sources, pain planetary nebulae. So this is a point that we can use definitely. From it's critical from the identification one point and the discovery, these two points. Now, if we want to understand the nebula and we want to go deeper in abundances in more details, this is something that I haven't touched yet. So but we have a lot of data, and we can start working on that.
The microphone here first, Noah, and then.
Yeah, I'm using BI, which is biological intelligence. And in my most recent paper on supernova remnant, I cite 2 papers from Psychology Journal. Because, no, really, I'm not joking. Because people in the supernova remnants ask me, why don't you use AI to identify symmetry or symmetrical structure in supernova remnants? So most of us make the best decision or the most important decision of the life just by inspecting by eyes. And this is choosing a mate. And it turns out that we are very sensitive to safe symmetry, because asymmetry in faces of the mate we are looking to might indicate some health problems. So we actually, and I cite psychological papers on that. So we are talking not about identifying spectra or some complicated structures. We are talking about identifying symmetry. And it turns out, really, I repeat it, that our eyes with brain are very, very sensitive to symmetry. So AI is important, but I trust my eyes more than I trust AI on identifying symmetrical structures. And I live now in this December 40 years with my wife, which I choose just by eyes. I didn't choose any AI to choose my wife. Just looking at her face, nothing else.
Yes, just to answer to Ursula. We're doing that actually more and more. There's more and more groups. We're going to that. That's mean using machine learning, as Stavros mentioned, for the discovery. For example, planetary nebulae, symbiotic stars, and stuff like that. So there's plenty of new big surveys coming or already there. So digital survey, the LSSC. So there's too much data to be doing by eyes. But parenthesis, I agree that for a big one, your eyes are better. But yes, so we're doing that. We're using machine learning as well for the chemistry, in the sense that to have a better estimation of abundances, of chemical abundances. So something that is still a bit difficult right now for planetary nebulae in particular, but with machine learning, I think that we're going to more with a lot of accurate, let's say, abundances. So yes, we're using it. So this is something that this is something that is not in the near future. This is something that's happening now. The issue right now is to have everything together. How do we mix together the morphology, the result that we have, the morphology, the result that we have with the kinematics? I don't know of any systematic analysis of kinematics of planetary nebulae, but this is something that can be done as well. So now the game is more regroup all the information to have a better sense of how planetary are. But as I said, all those studies are something that we are doing right now.
Okay, thanks for please.
Well, thank you, Noam, for a very Noam-like remark. With artificial intelligence as well as natural intelligence, the key point is training, education. We all know that with natural intelligence, training is jolly difficult, those of us who stand in front of a classroom. and would have been in the classroom previously. But how could we possibly, with what we have right now, start training an AI model? I have to make a start somewhere, but I have no idea where. Maybe someone else does.
Okay.
Okay, I agree with Vincent, and training is the most important thing with artificial intelligence. For instance, as Laurent spoke, I also use artificial machine learning techniques to compute well the signal. We both work with Christophe to compute ionization correlation factors in planetary nebula, but the training is made using photoionization models. And what if we are missing something? What if photoionization is not enough? What if there is something else there? So we are speeding up our calculations. We are doing a very nice work, but maybe we are losing physics in the process. So I think that we have to take care with that.
Yeah, perhaps comment on this is that this morning we're hearing about the fact that most of the things we know about for planetary nebulae, it's based on the optical or the bright, really bright set. So how you put together all the wavelengths, all the components, the different sizes and masses on the training, for instance. So we don't know yet all these details. So how can we train AA to do this work? I think that this is the key point, because I have been involved, though I'm not good at this, but I have been involved in works that are using machine learning for planetary nebulae, for symbiotic stars, and all the time we are limited. Even if you use only optical and sometimes optical and infrared, you are limited by the number of objects that you have very well observed for the training. But if you also consider that much bigger sizes and much colder matter on these objects, you are not taking these things into account. So how you can train to do the whole thing? This is the point. I mean, how we can get together to get, an effort of having a number of objects well characterized, but then you can follow this way. So I think that this is the key thing.
If I can make a comment on that, because 10 years ago I got interested in this training of, at that time, quite basic classifications to find out how to classify a planetary nebula. So I used the Google search, and I just put in an image of a planetary nebula it didn't know about. So it couldn't use its own archives, they classified it for me. It came back, it says it's an orange. Nowadays, I think we have self-training networks. And if you just want to know which morphologies go together in a group, it might give you surprising results. But give food for thought.
But your blind spots in bootstrapping are even worse. Right?
Yeah. Some natural intelligence has to be involved to filter the results. But it's, any more comments on the use of AI? Yeah.
One important thing is that we are human beings, so we always prefer to see beautiful images than complex diagrams. And you are talking about training AI, but it is also important to supervise AI. And if there are degeneracies between the models or between the parameters that we would like to compare, AI is not a magic black box and it will not resolve that.
I completely agree about the issue of training, and it's only as good as the training it gets. We've been playing around with AI and ML at Hong Kong ULSR for the last few years, and my wonderful PhD student Yushan Li did great work with using all known planetary nebulae from HASHTA in IFAS to train it on the VFAS survey and run it loose on that. It was now it's not my area, but she was using the swing transform and attention-seeking algorithms to do this work, and we applied it to VFAS plus data, found lots of candidates, and we went to observe them spectroscopically on a 2-meter telescope, and 85% of everything we looked at turned out to be planetary in terms of the emission lines and everything else that we got. So when you're looking in dense star fields, it was very good at finding stuff that when you're hunting by eye, you kind of miss because you're distracted by all the stars around in very dense star fields. And these things are like hidden next to stars or in the diffraction spikes of star areas and stuff like that. And so it found them quite effectively, and for the highest quality candidates, so a lot of them turned out to be PM. So that's actually quite encouraging. And the other thing I was thinking of the other day is that, as you know from Hash, we have these true, likely, possible classifications of PM. That's very objective, based on whole different strands of evidence where we think, okay, it's definitely because of this and blah, blah, blah. We have decision tree. But I'm thinking if we could do that more effectively and objectively through AI, that might like take out some of the fuzziness that we currently have in those classifications. Yeah.
There's no more comment than this, so that we can challenge.
Yes, so let's move on for psychology. Oh, Joel, would you
I
mind
just
to
had
comment?
a quick statement, the curation of data sets, I think is, you know, perhaps
From an observational perspective, I think curation of data sets is a nightmare for planetary nebulae where AI is concerned, and I don't know much about AI, just what the, you know, how problematic it's been, say, for folks working in biology or health sciences to take advantage of it. And their data sets are, you know, I think maybe simpler than ours, and that was really saying something.
Okay, well, maybe that's enough for the psychology of planetary nebulae. I'll to pick your mate. So, there was another question on the Slack. That was on what causes episodic mass loss, and that was a response to Son's talk. So, anyone who would like to comment on that?
Anyone beside me is.
No one. If you want to go first, please do so. What causes episodic mass loss?
This is a deep question because we are struggling with it for a long time since we saw the multiple shell and our rings are the two types of rings that we see on the sky, but there are also rings around jets that you see in active galactic nuclei and other objects. And so what causes episodic jet? There can be several reasons for that. It's mainly, I mean, accretion rate into the compact companion that launches the jets. But what determines the accretion rate or to the companion can be, first of all, eccentric orbit, so it's pseudo-periodic, like in Eta Carina, which is not a planetary nebula. It can be just instabilities in the accretion disk that cause it, like people think maybe in active galactic nuclei. And in our case, there is something very interesting that we didn't do enough to understand it. The AGB star and RGB, but mainly AGB star, and also a progenitor of the core collapse supernovae, have very vigorous and violent even convection envelope. So if there is a companion coming close to the surface of an AGB star, the AGB star is both pulsate very strongly and there are convective cells, huge convective cells that we see in some stars that we can resolve, like Betelgeuse and so on. So I think if we have a strong, close companion, the accretion rate onto the companion will be modified by eccentricity, the convective cell on the mass donor AGB stars, and different kind of instabilities. All of these can work together, some periodic, some not periodic. And it's very complicated to simulate, but since we see it also, this episodic mass loss and so on, the progenitor of core collapse supernovae, it is very important to study.
Comments?
It's actually a question. So when you guys now talk about episodic mass loss, what are you talking about? Something spherically symmetric, the entire star gives off, like from the AGB, I would say a thermal pulse-like detached shell structure? Or are we talking about very directed, much more collimated outflows, or are we talking clumps? I mean, what is it when you say episodic mass loss? Because that is an umbrella for a lot of different things, and then trying to give one answer, like one strand of the discussion, that doesn't seem very like likely to give an answer.
Now answer your question.
I don't have an answer. I'm asking you what you mean with episodic mass loss.
We all have a question. But no one was showing at the very beginning. There was one example that it was, well, I could precise episodic ejection in jets. It was HA29, I think. And in that case, it's a planetary nebulae with a binary in the center, no? But this was one case in the very beginning. But this is one of the possibilities for these episodic events.
Will be not an answer, an additional question is. Are we looking,
We do have.
so, the harder classification is its observation. If there's no interpretation, you look at it, you see something, you see classes of something, and then eventually you might try to interpret, like the OB classification of stars, they're really rooted in observation without interpretation, because you could be wrong with interpretation, and you want the classification to be useful forever, right? So maybe the next question is, okay, can we say episodic mass loss? Let's not even call it that, but we see some features like rings and shells, potentially those jets that look like there's many that come out from the same point and that move. So you have a series of observables, and then you say, well, clearly there's something that's happened with the periodicity, and that you might call it. And then so separate the observations and your markers to whatever you contribute.
More questions?
Yeah, it's a bit connected to what was mentioned before. When you mean episodic, you mean episodic over which kind of time space? Because that's the thing. Even HV winds are episodic winds. I mean, even giant star winds, red giant, normal red giants, they are episodic probably in the short time. So if you're looking at them over years, they are all episodic. So when you mean episodic, you mean episodic over which kind of time scale should they increase?
Yeah.
That's an important point to take into account.
And I would say in addition to that is when it happens. Is that during the HV wave loss, shortly after, a long way after, Dr. Hawkins called it jet lag. Yeah. Because I'm sure many of you will suffer at the moment.
We know what. You have.
About the missing elements, silicium carbide, magnesium sulfate, such kind of molecules are so hard. Well, you can create a bullet jacket using this, for example, and they are so they can be so cold in the environment that you cannot detect using advanced fast. Also, they for the vibrational modes you can catch data, but for rotational modes, then the substance is stuck on dust or the dust itself. You cannot obtain rotational modes. So they are so difficult. Talking about dust, so difficult to detect. So we cannot know the quantity, the exact quantity of this dust as long as we cannot detect us. Difficult. Just a comment from the view.
Yes, okay.
So coming back to the episodic mass ejecta, one thing also to take into account is what happens with these blobs, let's say, which are ejected afterwards. Because they evolve, they move outwards, they might interact with each other. So the kinematics of their post-ejection outburst does not necessarily go back to the periodic episodic outflows because they are altered on the way away from the central star. So that's also something that is complicated.
Sometimes when we see a jet-like feature and we see like different components there, so we think that there are like several episodes of mass loss of ejecta. Yeah, but sometimes what happens is that there are dynamics within the flow, and this is going to produce kinks and breaks in the flow. So what you see as several episodes is actually just a continuous flow of material, which is broken by the hydrodynamics.
Yeah, it's all the instabilities in the outflow, but if on both sides of the jet you see the same one, these are not instability.
Kind of.
How do they know what's done? So when you say episodic, it's not only just yes or no outflow, it can be variation. In Maslow, and what time scale we talked about can be tens of thousands of years if we have like thermal pulses, and it can be a few seconds if we have a wide dwarf accreting material. So, I mean, yeah, can change. So all time scale are good. Choose your time scale and where's the mechanism, look for observations.
And also there is all the instabilities that if you want to compare with models, you know, all the instabilities that happen in the gas, so in the outflow, so.
Yeah, but it will not be the same on both sides, this is because the stability is stochastic. If you see the same blobs on two sides, they must know about each other from the center.
Yeah, for example.
More questions? Answers?
Yeah, so I have a question about what Ravindra showed, this post RGB objects, and also related to this discussion now of episodic mass loss. Did you manage to constrain for how long those type of structures would be detected, Ravindra? And how the amount of post RGB object you see would compare to post AGB? I mean, was it possible to compare these two things?
Okay, so I guess your first question is, how long are you going to see these structures? But by these structures, do you mean the inner part which we are observing directly? The central part, or you're referring to the very extended stuff which we see in the part red?
I was wondering if then we will stop seeing them because they start the luminosity drops so much that then, well, you don't see it anymore, or?
Well, no, the luminosity is not dropping, it's going horizontally on the HR diagram. The post RGB objects, just like the post AGBs, are moving horizontally on in the HR diagram, so the luminosity is constant. Of course, eventually it'll start dropping, but it'll be just like post AGBs, they'll have time scales. So I suppose the post RGBs will have longer time scales because the post AGBs are the central stars now massive enough that it will evolve into much hotter temperatures faster, and then you have a regular planetary nebula. But for the post RGB is probably not clear. I think the time scales are much longer. And so whether you actually get a planetary nebula or not is something I don't know. I think it's unlikely. You get that. So there was a second. So you had a second question.
Can you then use the microphone?
Yes.
I was just wondering from the same type of data, you should also be able to find post HB sources that are more luminous and maybe have more dust around. And I was just wondering how the numbers compare, if anyone has looked at that or
Yeah, so in this spectroscopic survey which Kamath, Hans, and Nicolette did in the LMC and SMC, they found both post RGBs and post AGBs, and the main distribution feature between them is a luminosity. So there's certainly post AGBs with high luminosity and post RGBs with lower luminosity. Hans might remember the actual number, but I think there were comparable numbers of post RGBs and post AGBs. And in the little study which we did, we studied both post RGBs and post AGBs for comparison. And the main difference is the post AGBs have more, in the amount of dust that we detect, the most post AGBs have more dust than post dust. But again, that's a fraction of the total amount of dust which has been ejected. So we don't really know, we can't really compare the total amount of dust which has been ejected for either class of objects. We don't have a measure of this yet.
Following up with Ravindra, the post AGBs, we see nebulae around them. The post RGB, I guess the boomerang Are there others with visible nebulae around them?
Well, certainly for there are two objects in the SMC, which we now imaged with JWST, and both of them show bipolar nebulae. So those are, of course, we don't have to go to the measurement clouds now that with Gaia we can actually determine the luminosities of objects in the galaxy. There are presumably a lot of post-RGBs in the galaxy as well. And I think for some of them, we certainly find nebulosities. I think Arturo might have something to say about it.
With visible nebulae.
Using that as well.
I really haven't studied the post RGBs, but what I can say is most of those HSP images that is being shown in the past as post AGVs are not. So most of bipolar post AGV that you believe were post AGV were not. There are very few bipolar post AGVs.
So I think that works is very important.
So still on that topic, remember you just said there's more dust in the post AGB, so I hear the mantra often that post RGBs and post AGBs, there's some differences, but they're not so systematic, they're quite overlapping the two groups. And I'm interested in how they are made, right? There's a great difficulty in understanding those orbital elements from the point of view interaction that happened earlier. So the disks are very important to tell us what happened to these objects, because forming disks is not that easy in this angular momentum, and there's a lot of things you can measure. So the question when you say there's more dust in the post AGB, are the disks around post AGB binaries different, more massive, more extensive than in the post RGB?
Well, I think I can't give a robust answer to that because all the estimates we have of the masses in the disk and the shell components are based on modeling LCDs. And there's certain limitation to that. For the study that we did so far, which is for 8 post RGBs and 8 post AGBs, in general, both the shell and the drift masses are larger in the post AGBs than the post RGBs. But again, this study ignores the fact that a substantial amount of dust may be in bipolar lobes, like when we image this post RGB object in the JWST, we see these very prominent bipolar lobes, which so at the moment I don't think I can give you a robust answer to that.
Well, if you don't, I think that we still have
Yes.
Yeah. Perhaps we have questions from one of the speakers and the question that you didn't have opportunity to raise your thoughts.
That was Joel.
Well, yeah, you do have questions, so.
Always. Oh,
We have a number, but.
I'm trying to model good behavior for the junior researchers in the room by asking as naive questions as I possibly can. And they're genuinely naive. But I wanted to go back to Vanna's talk, which I think is fascinating because you get a lot of very precise information about the formation pathways of planetary nebulae by looking at these objects in clusters. And so, Vanna, where are you? So and I kind of hinted at it, but how many of these cases do you have which would say very accurate radial velocities and very good velocities for the potential host clusters?
Wait for the microphone, please.
Okay, so these are to identify that they are the identification until now the 5 cases in open clusters. They all have very good planetary nebula, very accurate planetary nebula radial velocities. So,
What sort of precision? When you say very good,
what we actually tried to find out was the spectrum graph, each spectrum are used to have a resolution and to have the specs that will get the rate of velocity better than 1 kilometers per second. One. Better than one. Though in some cases there are large errors.
Oh.
So the measurement errors can be the errors that we measured can be up to 7, I think, in some cases. And then we also have the precision of the cluster data. Again, with Gaia, things are getting better, but still, for example, in the last case, the cluster, the rate of velocity of the cluster gives like a standard deviation of 9 kilometers per second of the cluster. This is typically not expected. And it is from Gaia, so.
Thank you. That's an area that needs some work, I think, thanks to you.
And also about this work, I was wondering, when I were commenting that there is this offset in the relation you get with the, I don't know, 5 points you have there in the initial to final mass. And what are the ideas behind kind of the ideas to explain this gap?
The idea is that probably it's the models, they use different models. So I used for estimating the final masses, the evolutionary tracks by Marcelo, but then the other data from the white dwarfs, they use different models.
Marcelo, this is you.
Yeah.
Modeling in you specifically.
My first question would be, what the thing with modeling is, what tends to think that this is a problem of the final mass? But could it be could it be the case that it's just they are shifted to the right, not be to they're not shifted downward, but to the right of what they should be. So this would relate to the determination of the ages of the stellar cluster, which probably is very accurate. But then you have to translate that age into an initial mass, which was related to the question I made when you gave the presentation. So that would be the first thing. And then regarding the tracks, yeah, of course. Then we have to. I don't recall how do you determine the final mass from Minecraft? Is just by using the luminosity, or is it something else?
It's not some other case, the mud gates, so that's how
What? Sorry, then.
the age or the luminosity depends on the date.
It's the kinematic age of the nebula that is very important.
Okay.
Oh, wait, are we talking age of the nebula or age of the cluster?
Age
of the nebula.
So the age of the cluster is important for the initial mass. The age of the nebula is probably important for the final mass. Is it?
But regarding the initial mass, the white dwarfs, the combination relation is based on the same initial mass, isn't it?
Sorry, again.
It is the same initial mass that goes into the white dwarf initial final mass relation.
I don't.
So they also do white dwarfs in clusters, and they use an initial mass. It's the same initial mass.
Yeah. Yes.
Yeah. So that can't be offset.
From the initial mass, you mean? Yeah. So which models are you using for the initial mass of the?
I'm using the passive mass.
Okay. Probably the same. Yeah. There is an offset value. So I mean, if you look at the initial. The initial final mass relations of white dwarfs, which is probably the most accurate we have. The most reliable, still has a huge spread. So the error bars of the initial mass are usually quite high, particularly when you go to the massive object. So I don't know.
Just to say that I think using kinematical ages as a white dwarf age is really dangerous, right? Because kinematical ages are not necessarily representative. They give you a minimum age. Oh, I thought. No, kinematical from the nebula, no? Because the expansion can slow, and also in the models, when you start the post AGB track, it's totally arbitrary. So, and for young things at least, it can make a very big difference.
Yeah.
Yeah. I think it would be like, sorry, I saw. More than one and it could do this.
I just wanted to say that Simi is gonna tell you on Wednesday that the kinematical ages and evolutionary ages that you derive from the tracks based on the stellar parameters of central stars do not really agree. So I would like to support what Dave was saying. Kinematical ages are not reliable, or I would not trust them.
Yeah, other two people that are right there, Arturo and someone else at Stavros, and then I think that was the bit there.
Yeah, I agree with this in mathematical ages. As a comparison, when you use different ions, nitrogen 2, oxygen 3, the H's are completely different.
Yeah.
Very quick comment. I understand that there are a lot of assumptions, a lot of problems. Several people said that, but if Vanna in the plot that she showed, there are 5 objects for her work and more others. Does it work to do the analysis on the same assumption for all these objects in the plot and see if there is this offset? No, is it possible?
No. Okay. The thing is, I mean, if you are referring to the white dwarf versus the planetary nebulae, you mean the comparison between the two?
The observed points.
Yes, but the observed points for the white dwarfs also.
Oh, yes.
The problem is that probably the determination of the final mass for the white dwarfs is very different. Because you don't rely on any kind of expansion age or anything like that. I mean, in a way, you rely on the location on the HR diagram. So how long did it take them to cool down to the effective temperature and gravity that they have right now? So it's a very completely different approach to get the final mass. So yeah, I agree that if for the planetary nebulae the expansion age is being used, probably there is a lot of systematics going on. And probably even which kind of tracks you are using will make a difference. And as he said also, where are you starting to count that age? Yes, because the transition from, let's say, the fast evolution of the planet and the central star is the fast heating up. But then you have this gap in between the HEV and the beginning of the heat. The object is already hot, which is quite unknown because it depends on winds and the both HEV phase, and this is nobody knows.
Okay, I think we should stop there. Because we're out of time. But I would say let's first thank our speakers again. And second, I think the person might have run the microphone deserves to know.
Thank you very much to Robbie. Now we are going to go for lunch. Here is the map. So we are going to Estación Experimental Saving. And this is the path we are going to follow. So there is going to be a few leaders like Jesus or myself or Fernando over there. So we're going to take you there. But they have agreed to open us the back door, which is here. So usually the walking is going to be shorter. We get through this gate and then get to the cafeteria, which is over there. Okay. And remember to bring your badge.
Yeah,